Hello, this is a review of item number 9.14 from our text. Um, Pardon me for the loss of voice, but I want to walk you through this problem so you have it as an example for the exam coming up. This problem kind of sums up the entire chapter here, which is a pivotal point really in this course. So I do find it important to walk through. The scenario is the fact that, or the premise that they have a random sample of 144 children taken from a local population of grade school students. And they were surveying them to find out the number of hours that they watched television per week. And so what I have over here is in the black curve is a curve that's representing the all possible outcomes for the individual students in the area, in the town. And it may be normally distributed, it may not. To be honest with you, we don't know. But we do know is that a random sample of 144 students were selected out of that group. And the question now is, what can we say about the sampling distribution? Well, the sampling distribution, just to make sure we're all clear with it, is not the distribution of all the individual students and the number of hours that they watch. The sampling distribution is the distribution of all of the possible combinations of random samples of size 144 that we can select out of that population. So if we continuously kept selecting sample sizes of 144 students and found out the average number of hours per week they watched and graphed those averages, that graph is going to be approximately normal regardless of whether or not the original population is normally distributed or not. And that's due to the fact that we have a sample size greater than 30. We can say then that the sampling distribution is approximately normally distributed, just like this green distribution right here. And the next question is, assume that the standard deviation of the population is 8 hours. What can be said about the sampling distribution? Well, what's happening here is that, again, this sampling distribution is the distribution of all the different possible averages from samples of size of 144 out of the group. So if we just plotted those averages, the averages of those samples are not going to be spread out as much as the original population of individual students. Their averages, and if I kept taking averages of groups of 144 students, the averages are going to be clumped together real tight. And that tightness is defined by this formula, which is the formula for the standard error of the sampling distributions. And what it does is it takes the population standard deviation, in this case 8, and divides it by the square root of the sample size. So we had the sample size of 144 from the first part. And we bring that down, that's our n. And they are giving us the standard deviation of the population of 8. So 8 divided by the square root of 144. Square root of 144 is 12. So 8 divided by 12 is approximately 0.67. We're going to round it 2 decimal places. This is going to be the increments, the value of the increments here of this new green distribution. So the black distribution is of the population, and that had a standard deviation of 8. So each of these black increments are worth 8 points. This green one is going to be of the sampling distribution, and their increments are much tighter together, in this case 0.67. Next question says, assume that the mean is 21. This is again of the whole population. Well, if the mean of the whole population is 21, then the central limit theorem tells us that the mean of all the possible samples that we can select out of that is also going to be 21. So this new sample distribution here is centered about the same mean, or 21, as the original population. Next question says, roughly speaking, samples means should deviate on average about how many hours from the mean of the sampling distribution and of the mean of the population. Well, if the mean of the sampling distribution and the mean of the population are going to be the same, both being 21, then we know that the standard error is 0.67. Then we can say that, roughly speaking, the means of all the different samples are going to deviate on average about 0.67 hours from the mean. That's what that means. And then the last question, which is, again, a little foreshadowing for what we're going to have for the rest of the course, is a statement stating this. About 95% of the sample means in the sampling distribution, again, not of the whole population, but in the sampling distribution, should be between what number of hours and what number of hours, or what interval can we expect 95% of all of the means generated by the different samples of size of 144. What interval is going to contain that 95%? And we're going to take this from a few chapters ago, and instead of taking the mean and adding and subtracting the z-score times the original standard deviation, we're going to take the mean and add or subtract the standard deviation times the new standard error. The question is then, where do we get the z-score of 1.96? Well, if 95% of the population is centered about the mean, here, then we can expect that half of that 95% is going to be on one side of the mean and half is going to be on the other. If 95% converts to 0.95, we divide that by 2 to get 0.4750, or a proportion of 0.4750 of the population is going to be between here at the mean and the upper limit of my increment. In the back of the book, if we look at the normal curve table and we look under the area of 0.4750, and again, that's an area from a certain increment to the mean, that gives us a z-score of 1.96. For purposes of this problem, you could have said 2, because roughly about 95% of the population is going to fall within 2 standard deviations. So whether you use the z-score of 2 or you want more precise with 1.96, we plug that into the formula. Now remember, this plus or minus means we're going to do this twice. We're going to go 21 plus 1.96 times 0.67. That'll give us the value of 22.31, roughly right around here. And then 21 minus 1.96 times 0.67, or 19.69. And if you notice, these two values are equally distant from the mean. They're on either side of the mean. So we're going to say that 95% of the population of all the sample means in the sampling distribution should be between these two values. That's how you do that problem, 9.14, and that should help you with one of the last problems on our test. Thank you.